Today we use calculus to solve for a simultaneous move Nash equilibrium where we have 3 players. Why don't you pause this video and see if you can make any progress on this problem working on your own. Let's start with player 1. Player 1 maximizes his payoff treating B and C as constants. Now, when you treat B and C as constants and you take the derivative of this goes away. What's happening with player 1 is saying, you know, I like the fact that I get B plus C squared added into my payoff, but I get that no matter what I do, and I have no control over B plus C squared. My choice of A has no effect over B plus C squared. Yes, what the other players perceive I'll pick as A might influence B plus C squared, but what I actually pick as B plus C squared can have no influence. What I actually pick as A can have no influence over B plus C squared. So when player 1 maximizes his payoff, he'll ignore this when deciding his optimal strategy. And that's what the rules of calculus say. If B plus C squared are constants, this goes away. We get first order conditions of 2 minus 2a equals 0, which are solved at a equals 1. Then we check the second derivative to make sure that we found a maximum and not a minimum. We take the derivative of this, we get negative 2, which is negative, so we found a maximum. We solve first order conditions by setting a equal to 1, and that turns out is a dominant strategy. It's a dominant strategy because it gives player 1 a higher payoff no matter what the other 2 players are doing. Because there's no B or C in here, you know player 1 wants to pick A equals 1 regardless of what the other players are doing, and you know, because this solves the maximization problem, that A equals 1 gives you a strictly higher payoff than setting A equal to anything else. The other 2 players will eventually realize that player 1 has an optimal strategy of setting A equal 1, and they'll count on him doing this. All right, now let's turn to player 2. Okay, player 2 maximizes his payoff, treating A and C as constants. Now, when player 2 maximizes his payoff, he's going to ignore this. This is, by the normal rules of calculus, you take the derivative, this goes away. But also player 2, will be thrilled to get the 30 added to his payoff, but we'll say I get the 30 no matter what. My choice of B has no effect on this 30, so I'm going to ignore that 30 when picking my optimal B. And that's what the normal, calculus maximization will do. Take the derivative of this, treating B as the variable, but A and C as constants, gives you this next line, 4AC minus 2B. Set it equal to 0 for first order conditions. Then you solve for B, and this gives you either the maximum or minimum, depending on the second derivative. Well, we take the derivative of this, we get the number negative 2, which is negative. That means that solving the first order conditions is giving you a maximum. This is player 2's reaction function. Player 2 does not have a dominant strategy because his best strategy is dependent upon what the other players do. Player 2 doesn't know what to do until he's figured out what player 1 and 3 will do. But once he knows what player 1 and 3 will do, then this, which is reaction function, will tell him what he should do. Once he knows A and C, he says, well, my optimal strategy is to double the product of A and C. All right, now let's move on to player 3. Player 3 maximizes his payoff, treating A and B as constants. We take the derivative using the normal rules of calculus, and we get this thing. Setting it equal to 0 gives us our first order conditions. We solve for that, and this is what we get here. Now we've got to check second order conditions. If we take the derivative of this with respect to C, treating A and B as constants, we get negative 4A. And we can't be sure if that's positive or negative, but then we can remember, oh wait, fortunately, player 1 has a dominant strategy is setting A equal to 1, which will mean that this will be a negative. Now, if we weren't sure that player 1 was going to set A equal to a positive number, this would be a lot more complicated. We'd have to work through the different cases. But I made this relatively easy by giving player 1 a dominant strategy of A equals 1, so we know for player 3 that this is going to give him a maximization. This is going to give him a maximum and not a minimum. Okay, now for the Nash equilibrium, we have 3 conditions that have to be met. Player 1 will regret if he doesn't set A equal to 1. You always regret not playing your dominant strategy. Player 2 will regret not setting B equal to 2AC. And player 3 will regret not setting C equal to this thing. So we've got 3 necessary conditions for a Nash equilibrium. And if you do some simple algebra, you should see that they're satisfied if and only if A equals 1, B equals 2, and C equals 1. So we found our Nash equilibrium at these values. Thank you.